Assalamu alaikum everyone. Welcome to our project presentation session of EEE 426. We are group 4 with you to present our project demonstration. We are thankful to our course teacher Shahid Ahmed sir and Talib Mahmoud sir for giving us the floor and being supportive throughout the project session. Well, here is our project title. Our project is basically detecting chest diseases from chest X-ray using deep learning. So this will be our segment throughout the presentation. At first, a problem description, basically what we want to work about to solve it, then description of the dataset the problem handles, then the baseline will go for, then different phase of the experimental result to choose the proposed methodology, and finally includes the pathways of future research. In clinical practice, diagnosing the chest X-ray images is heavily dependent on radiologists' expertise with at least years of professional experience. The classification task is highly challenging for computer-aided screening due to the low resolution and poor specificity of chest X-ray images. Well, we state that a multi-level classification problem for thoracic disease that detects if one or multiple diseases are presented in each chest X-ray image to effectively realize the discriminative information from pathological regions and avoid the affection of normal regions. Moving on to the dataset, CheckSpurt is a large public dataset for chest radiograph interpretation, consisting of over 0.2 million chest radiographs of approximately 65,000 positive, negative, or uncertain. We report the prevalences of the level for the different observation in table. No finding and support devices observation was intended to capture the absence of all pathologies, and for the rest of the images, there can be 14 observations on a single image. There will be positive and negative as well as uncertainty that basically represents ambiguity. Output of the leveler when run on a report sample from dataset. In this case, the leveler correctly extracts all of the mentions in the report and classifies the uncertainties and negations. Here 0, 1 and U respectively denotes negative, positive and uncertainty. Moving on to the next presenter.
Hello, this is Prashant Datto. I am here to present the first baseline model of our project. Our first baseline model is probabilistic M-pooling and novel pooling operation for lesion localization. In this network, a fully convolutional neural network, to be specific, DenseNet 1-to-1 is used to generate the feature map. Each feature embedding within the feature map goes through the FC layer for fully connected layer to generate the class activation score, which are passed through the sigmoid to generate the probability score. These probability scores are normalized to attention weights. These attention weights are used to pool the original feature map by weighted average pooling. In this problem, 5 pathologies are classified. We can see that PChem pooling can perform better in classifying edema and performs poorly in classifying cardiomegaly. Comparison of AUC mean AUC score, we can see that the reported mean AUC score is better than the experimental result due to the larger image size. Our second baseline model is a journal paper which incorporates hierarchical dependency and label smoothing in its training method. Two major novelty of this model is conditional training process based on predefined disease hierarchy, which is presented in the form of a tree. Due to this, model can learn dependency among labels. Next, label regularization method, which is implemented by mapping each uncertainty label to a random number. What is hierarchical dependency? Hierarchical dependency is predefined by the radiologist. Here the root nodes or parent node correspond to the most general class. Opacity is like a root node, and leaf node denotes a specific class like pneumonia. This horizontal bar plot here represents class-wise AUC score. Our experimental result shows that it performs good on consolidation, whereas the reported score in the paper performs good in pleural effusion. From the column chart, we can see that the reported AUC score is better than the experimental result because in this AUC score is obtained by using ensemble model, whereas in experiment we have used only single model. Moving on to the next presenter.
Our target was to beat the baseline score of 0.892, and for that we did a lot of experiments. To understand better, we have distributed all of our experiments in 4 distinct phases. In phase 1, we are looked at the different backbone architectures such as DenseNet 201, DenseNet 169, Inception version 3, and their performance on the datasheet. Here we can see from the graph that the Inception version 3 architecture had reproduced the value of 0.892, which is a promising result, but not the target score of above 0.892. Then in phase 2, move toward different attention modules such as class activation module, feature pyramid attention, and special attention module SAM. Here we can see that the CAM attention map's performance is not up to the mark, whereas the SAM attention map gives the increment of the baseline score, producing AUC score of 0.89. SAM attention model and Inception version 3 model work progressively well in our previous phase experiments. So in phase 3, we have implemented both the SAM attention model and Inception improve our previous base score of 0.893. So we have implemented this attention module and backbone model with the increased image size of 320 and 320 to check if this can produce target results, but it did not improve either. For the next phase of our experiments, we have changed the positional weights as from the previous experiments we saw that class 1 and 4 does not perform well in terms of accuracy score. So we have changed the class 1 and 4 positional weights to see if this can achieve our target. But the best possible result we have got is 0.893, which was our previous best.
For our next step, we decided to merge the idea of pick and pulling into some other models. The first idea that we incorporated was from a paper named Diagnose Like a Radiologist, AGCNN for Thorax Disease Classification. In this paper, they have used three-branch attention-guided convolution neural network. They first trained a global CNN branch using raw images from dataset, which they are calling global images. Then, guided by the attention heat map generated from the global branch, they created a mask to crop a discriminative region from the global image. This crop portion is used for training a local CNN branch. Lastly, they concatenate the last pooling layers of each branches and create the fusion branch. Here we can see each of the global and local branch is connected to a max pooling layer. Our attempt was to replace this pooling layer with pick and pooling and see if it gives any better result. But unfortunately, that also did not give us any fruitful result. Next, we have considered the paper Waning Feature of Lung and Heart Region for Thoracic Disease Classification. We can see the framework here. There is a feature structure with a multi-scale attention module which generates a global attention map from a chest X-ray. A pixel segmentation model locates the lung and heart region to binarize a mask in which pixels are 1 for lung and heart and 0 for other regions. A local attention map focusing on the lung and heart region is formed by introducing a logical AND operator on the mask and the global attention map. This local attention map contains features of the pathological area and suppress the normal region. Merging this method with our previous one gives us a slightly better result. The next speaker will explain the process of merging in detail.
Now we will look at the various experiments that we conducted on phase 4 of our work. As mentioned previously, merging with the CH-PCR method gave better results, so therefore we hold on to that. Firstly, we trained the merge model with fit and weight, which gained results. Then we attached the SAM attention module into our framework, which was our main initiative from phase 2 experiments. The best result we achieved by attaching positional weights in our training scheme that we experimented on phase 3 and changing the placement of margin. Then finally, using a scheduler helped increase the result a bit more. The final result gave us a mean AUC of 0.897. In this slide, we see our proposed model architecture. We are using a segmentation-based unit model to segment the lung and heart from X-ray images, then merging that binary map with feature pooling, whereas previously we were merging with the feature map. As for future work, we want to share some good ideas that we could not try out during this project due to the time constraint. For starter, we want to change the position of the SAM attention module in our architecture. It makes more sense to use it directly onto image rather than using on feature map. Secondly, we saw that our model is performing very poor on the lateral view images. To handle that, we can use an image classifier that can distinguish between lateral and frontal view and then pass the image accordingly to the corresponding model specifically trained for that. Finally, we want to try out pulling the unit out of our proposed method and then using it to color code the lung and heart region. Then we would use that image along with the grayscale raw image together to create a 4-channel image and train the network with that. Thank you for giving us a patient hearing. Please let us know if you have any questions.